All right, let's dive into the hidden world inside a chemical reaction. A world where everything looks perfectly still, but underneath the surface, it's actually in a constant state of motion. We call this homogeneous equilibrium. It's this perfect balance where everything exists in one single uniform mixture. But how do we actually measure this balance? Let's find out. So picture a closed system like this one. Inside, you've got molecules in a constant, kind of frenetic dance. They're reacting forwards and backwards over and over again. Now, when the speed of those opposing reactions become equal, the system hits what we call a dynamic equilibrium. To us, on the outside, it looks like nothing's happening, but it's a total whirlwind of activity. So that's the big question, right? How do we measure this? How can we actually describe this perfect balance? Using math. Here's our game plan for today. First, we're going to learn the two languages chemists use to talk about this balance. Then, we'll build the mathematical bridge that lets us translate between them. After that, we'll put that bridge to the test with some actual calculations, and finally, we'll tie it all together with one big master schematic that shows how everything connects. All right, first things first. To describe this equilibrium, chemists use two really key measurements. You can think of them as two different ways of saying the exact same thing. We call them the equilibrium constants, Kc and Kp. The big idea today is homogeneous equilibrium, and that word homogeneous is the key. It literally means the same throughout. It's telling us that all the reactants and all the products are perfectly mixed up together in a single uniform phase. So there are no layers, no separate parts, just one seamless system. Okay, check these out, two perfect examples. Over on the left, you've got the famous Haber process for making ammonia. You've got nitrogen gas, hydrogen gas, and ammonia gas. It's all happening in a single gaseous phase. Then, on the right, we've got a reaction where everything is dissolved in water, a single aqueous solution. See, both are classic examples of homogeneous equilibria. So this brings us to those two languages we use to measure this balance. The first one is Kc, which describes the balance using molar concentration, which is basically, how many moles of something are packed into a liter. It's super versatile. It works for dissolved solutions and for gases. The second language is Kp, and this one is only for gases. It measures the balance in terms of the partial pressure that each gas is exerting, so two different ways of looking at the very same state of equilibrium. Okay, so if we have these two different languages, Kr and a Kp, there has to be a way to translate between them, right? Well, that's exactly what we're going to do now. We're going to build the mathematical bridge that connects the world of concentration with the world of pressure. And our main tool for this job is the ideal gas law, PV equals nRT. Now watch this, it's pretty cool. If we just rearrange it a tiny bit, divide both sides by volume, V, you get pressure, P, on one side, and N over V on the other. But wait a second, what is N over V? Moles divided by volume? That's the definition of concentration, C. And just like that, the ideal gas law gives us a direct link. Pressure is just concentration times RT. This little equation is our Rosetta Stone. Now, this is the standard way we write out the expression for Kp. It looks a little intimidating, but it's just a ratio. You put the partial pressures of the products on top and the partial pressures of the reactants on the bottom. And each one is raised to the power of its coefficient from the balanced equation. So our goal here is to replace every single P for pressure in this equation with our new expression that uses C for concentration. And now for the key move. We take our new tool, that P equals CRT equation, and we substitute it into the Kp expression for every single pressure term. Yeah, at first it looks like a total mess of letters, but then we start to clean it up. We group all the concentration terms together, and we group all the RT terms together. And when the dust settles, look what's hiding right there in that blue box. It's the ratio of product concentrations to reactant concentrations. That is the exact definition of Kc. And that move right there gives us our amazing bridge equation. Kp equals Kc times the quantity RT, all raised to the power of delta N. Now, that little symbol, delta N, is the secret sauce. It's just the change in the number of moles of gas as the reaction happens. All you do is take the moles of gas products and subtract the moles of gas reactants. You can see it on the scale here. If the number of gas molecules doesn't change, then delta N is 0, and Kp is exactly the same as Kc's. Okay. So we've got the theory, we've got the equations. Now it's time to see how this stuff actually works in practice. Let's get our hands dirty and solve a few problems. Let's start with an easy one. Imagine this reaction has reached equilibrium, and we've got our lab equipment out, and we can just measure the concentration of everything in the flask. Well, Once we have those final numbers, calculating Kc is as simple as plugging them into the formula. Products on top, reactants on the bottom. In this case, the math gives us a Kc value of 1.79. Easy peasy.
So that was pretty straightforward. But chemistry isn't always so nice to us, is it? What happens in a more realistic situation where we only know what we started with and we have to figure out the final equilibrium concentrations all by ourselves?
To solve this kind of problem, we use a simple but really powerful tool called an ice matrix. It helps us keep everything organized. ICE stands for initial concentrations that change as the reaction happens, and the final equilibrium state. So as you see here, we start with 0.1 molar of our reactants and, well, 0 of our products. As the reaction moves forward, some amount X of the reactants gets used up, and that same amount X of the products gets created. And that leaves us with our final equilibrium expressions down there at the bottom. So now we plug these equilibrium expressions into the formula for Kc. And since we already know the value of Kc, we can solve for X. Now, this often ends up giving us a quadratic equation, which means we get two possible answers. And this is where we have to think like chemists, not just mathematicians. The math spits out two values for X, 0.067 and 0.194. But hold on, look back at where we started. We only began with 0.1 molar of reactants. It's physically impossible for the reaction to use up more than we started with, right? So we throw out the impossible answer, and that leaves us with the correct value for X, 0.067. So now we know how to find Kc. The next logical step is to use our awesome bridge equation to translate that value into its pressure-based twin, Kp. And the process is just a simple three-step recipe. First, you calculate the change in the number of moles of gas, delta N. Second, you write down our bridge equation, Kp equals KCRT delta N. And third, you just plug in all the numbers and do the math to find the answer. Let's run through our three-step recipe with this reaction here. Step 1, find delta N. Okay, we end with 3 moles of gas and we started with 2, so the change is just 1. Step 2, we grab our bridge equation. And step 3, we plug in our known values for Kc, the gas constant R, and the temperature. A quick punch into the calculator and we've got our answer. Kp is 0.033. Done. Whew! We have covered a lot of ground, from the basic definitions all the way to some pretty complex calculations. So now it's time to zoom out and see how all these pieces fit together into one big picture. And this master schematic puts everything in its place. It's so cool. On one side, you've got the Kc domain, which operates in the language of concentration. On the other side, you have the Kp domain, which uses the language of pressure. In connecting them, that's our universal bridge, our master equation, the translator between the two worlds. And it's all supported by the constants hub, those fundamental values like R that make the whole system work. So, this table basically summarizes the entire toolkit we've built today. We started with that fundamental link between pressure and concentration. We defined our two constants, Kc for concentration and Kp for pressure. We built the incredible bridge equation to convert between them. And we identified delta N as that critical factor that really powers the whole conversion. Okay, one last and super critical point. That K and Kp and Kc, it isn't truly constant. It's actually highly dependent on temperature. Just look at these two real-world examples. For the Haber process, which is exothermic, cranking up the temperature makes Kp plummet, meaning you get way less product. But for the endothermic formation of nitrogen dioxide, increasing the temperature makes Kp skyrocket. Temperature is like a powerful lever that lets you control the outcome of a reaction. And that brings us to our final thought. The Haber process, which we've talked about a few times, it's the process that literally feeds a huge chunk of the world's population by producing fertilizer. So based on everything we've learned today about pressure, concentration, and temperature, how would you, as an engineer, tweak the conditions to squeeze out the most ammonia possible? It's these principles right here that turn chemical theory into world-changing technology.